My name is Sanji Fernando. I'm with Optum Labs. Optum Labs is a small part of UnitedHealth Group, and I'll explain a little bit more about what we do. Before I enter into my talk, when I put this together, there was an addition of with GPUs to the title. And so I figured I'd just cover that off really quickly at the beginning, but also happy to answer any questions about how GPUs play a role in the models we train and build. For the most part, as model designers and builders, we rarely see the GPUs in the sense that we work within containers. It's relatively abstracted. There are some idiosyncrasies with the different frameworks we use where sometimes not all the GPUs that are available to us can be used for training. But the way we see it is that it just makes training faster relative to CPU. And we have a mixture of hardware solutions that we leverage both from NVIDIA as well as Dell and HP. The Dell and HP solutions actually have NVIDIA cards in them, so we're essentially all using NVIDIA GPUs for our training. But I'm happy to answer any questions about that. But my talk is probably going to focus more on how we aligned on where to use deep learning in healthcare and our process for training and designing models for use in healthcare. So before I begin, let me share a little bit about Optum. We are a very large health services company that I'm sure many of you are not familiar with. Our brand is really not well recognized. But we have this sort of vast array of participants in our healthcare system that we touch every day. We are now roughly one half of UnitedHealth Group. The other half of Health Group that you might be more familiar with is UnitedHealthcare. UnitedHealthcare is the largest private health insurer here in the US and is almost a $202 billion company. Optum is about a $90 billion company, and we are well less known, but we have a myriad of services that support healthcare across the US. And so with this slide, I love this slide because we almost touch every aspect of the US healthcare system today. We work with providers. We actually help them submitting claims back to payers as part of revenue cycle management. We consult with them on how to improve their operations. We work with employers who may or may not be customers of UnitedHealthcare for health insurance, but we help them manage the health and wellness of the populations that they're trying to serve, employees and their families. We work with the plans themselves. We have lots of administrative capabilities that help you process claims in the US. We work with pharmaceuticals and life sciences companies because we have an enormous amount of data about how their products and services and capabilities are being used in the real world. And we work with both state and federal governments, both here in the US as well as in other countries. I found very few examples where there are not single-payer healthcare systems outside the US. And so we work with many of those organizations in both the UK and Brazil and other geographies. But here in the US, we work with the Centers for Medicare and Medicaid. We work with many of the state governments, both in supporting all their citizens as well as their citizens who might be supported through Medicaid programs. So we touch so many aspects of the system today. Again, we're relatively less well known, but that's the basis of sort of my points of view today that I'll share around healthcare and what's happening in the application of deep learning. So some of you may be familiar with this, others may not, but there have been amazing breakthroughs in the use of deep learning in healthcare, mainly on the academic side. Numerous papers have been published almost weekly on novel uses for deep learning. We've seen some really amazing stuff from companies like Google and others where they've taken deep learning neural networks that have been trained to recognize objects and images and retrain them to look at medical imaging, skin lesions, look at diabetic retinopathy, some really amazing breakthroughs that we think eventually will make them into the US sort of set of clinical practices. These models, and if you're not familiar with deep learning, are these vast multi-layered arrays of neural networks. And they do a great job classifying these images. And whether it's healthcare images or just general images, trying to pick a cat in a picture, it does a great job identifying these discrete objects in the image. But it doesn't give us a lot of interpretability today as to what drove that classification. There are some frameworks that are helping us get sort of a better sense of what's happening inside the deep learning neural network that reflects why it's classifying an image a certain way. But without that really strong interpretability, it becomes a bit of a challenge to take these tools and say, we're going to automate a clinical decision. We're going to take a decision or a clinical diagnosis and rely on a software model to make that designation. For clinicians who've been trained, who work in the US healthcare system today, that lack of interpretability is a big challenge for them when they think about all the transparency and control and accountability they want in clinical decision making. So that ends up being a little bit of a barrier. We hope it'll be overcome by a combination of regulatory changes as well as improvements in technology. But as of sort of today, that becomes a bit of a barrier. There's another challenge we have in healthcare data that is probably less well known, where we have generally very poorly labeled data. In and around 2008, as the or the ARA, the American Recovery Act, funded a lot of the expansion in the use of electronic medical records, we saw that adopted widely across the US. But in the rush to adopt that, there weren't necessarily all the controls and capabilities to normalize or standardize that data. Diagnoses can be misdiagnosed or underdiagnosed typically in these systems. And so when we think about training deep learning neural networks, we have a labeling problem as well. And so if you were to try to make a clinical decision on a model that was trained with poorly labeled data that is also less interpretable, that also represents a challenge for us. And so these are some of the things we are seeing in the market today. As exciting as it is with some of the academic work on what's happening in clinical diagnosis, and I wholly believe that we will get there, that AI will be a part of the clinical diagnosis process in the future. Today, there's probably work ahead of us to accomplish that. I love this quote because I think this is just simply reflective of what I do. I work at this cool lab, we've got cool offices, but I work on the completely unsexy part of healthcare, which is administrative processes. And this quote from Brian Roberts is really reflective of how we focus our time. Much of the healthcare that you receive, if any of you are here in the US, as I assume most of you are, relies on a lot of administrative processes between your provider, your employer, and the insurer or payer that provides the insurance to fund your healthcare. These administrative processes can be an extremely large portion of the costs here in the US. In 2014, there was a study that estimated them to be as high as 25% of our total healthcare costs. And so these administrative processes are a burden on our healthcare system, but extremely important for us to get the kind of quality and care that we all want to receive. And our interest is now to see if we can apply things like deep learning to really help us rethink how we do some of those administrative things. And I'll explain why that's interesting. What am I talking about? Claims adjudication is the process in which an insurer or a payer might decide how to pay out your claim. And while most claims are paid out based on what's billed by a provider, many do run into fall out of the process because there's a lack of documentation or maybe there's a missing piece of information. information, or maybe there's a question about the diagnosis and how it was, how the provider may come about with a diagnosis. Medical chart reviews. We review medical charts to support many of these processes as well, to help us decide, are you getting the highest quality care from your provider today? Are they billing the appropriate amount to you as a receiver of healthcare as well as the insurer? We help the providers think about how they submit their claims for payment. And that's an important part of their process called revenue cycle management. And we study all this data to better understand how we could communicate with large populations to help them achieve better results and hopefully better care and possibly reduce the total cost burden for them. So these are all important administrative processes, often that are extremely important, but we don't have the kind of clinical, the burden of accuracy and thoughtfulness that's required in a clinical diagnosis. These are administrative processes that are well past your care that you receive. It's simply us having a better way to ensure that we reimburse all the important parties in this process correctly. And so some of the things we think about, obviously the patient-provider experience. STARS and HEDIS are important quality measures that CMS helps CMS understand how you, as a Medicare recipient, might be receiving healthcare in the U.S. We think about claims and payment administration. We think about value-based reimbursement models. This is where, in partnership with your provider, there's a negotiation on what the total cost of your care would be. And so you could imagine if someone has sort of had a fixed amount to spend on your care, we don't want them to underspend. We want you to receive the appropriate amount of care. But how can we do that? We end up reviewing charts, we review the histories that you might have to make sure you're receiving the right care. And then we help with providers making sure they're appropriately reimbursed for the care they may be delivering to you. So these are all really unsexy problems, but they have some very interesting aspects with regard to AI that we think make them very well suited for trained neural networks. So how does this work today? A lot of the things I talked about, a lot of the claims we review, a lot of charts we review, for the last 10 years, companies like Optum, as well as other organizations, have actually recruited and hired some very skilled healthcare professionals to actually read these materials, to actually sample them and review them, help support the appropriate level of reimbursement by looking at the medical data and making a judgment about what was done. This is a well-structured process that's defined by regulations both at the federal and state level, but these are extremely manual steps. You could imagine someone attending med school for 4 years, that person's time is extremely valuable, but it's important enough that we ask them to review these charts and help provide a second set of eyes on some of these decisions. And that helps us confirm diagnoses. It helps us make a case that this was complex enough to be reimbursed at a certain level. All of this, we hope, is allowing us to deliver great quality care, but at an appropriate price and cost. And so today, that's part of that administrative burden I talked about. So what's interesting is over these last 10 or 15 years, we have also assembled a great amount of well-labeled data from these skilled professionals. Their decisions about how appropriate care was, how appropriate a decision was, what was the diagnosis here, was there something that might have been missed in the initial encounter with the patient. All that's reflected in almost 10, now 20 years of data that we've accumulated as an enterprise. And so that's what's really sparked our interest around how we could take something like deep learning and explore training models that might replicate some of these processes. One example of this that we've actually worked on is we have a large business called Physician Advisory Services, where for large hospital systems, we'll provide a second set of eyes on a medical chart. We employ lots of physicians who are available to review these charts. We've created a great workflow system where we can bring the charts in from the provider. We can present them in a workflow tool to both case managers and then physicians to review the charts. And all this helps us reduce the costs with regard to what a payer might have to spend for your care, as well as reduce the likelihood that the initial claim from the provider will be denied because maybe some piece of information or a justification was missing in that chart. And what we rely on a lot in these charts is actually, and you can see snippets of it here, it's very hard to see, the physician notes from the EMR, which is this crazy shorthand that reflects content-specific words, very little sentence structure, sometimes because of the way EMR systems work, actually chunks of HTML markup, all interspersed in these unstructured text fields. And so while we've invested a great deal in sort of traditional natural language processing to parse through some of this text, it's challenging. If we don't have the ontology right, if we don't have the vernacular right, sometimes we see changes in use of abbreviations by hospital, by physician group. All of that nuance is in these notes, but not always reflected in the rules or the ontologies that we might try to apply to these physician notes. So what we did was we said, given some of the sentiment analysis that's possible with deep learning, some of the techniques of using RNNs and LSTMs, are you guys all familiar with those generally? RNNs and LSTMs are types of deep learning neural networks. They're really well suited for looking at strings of text, in part because as you pass the text through the deep learning model, the nodes of that network have a little bit of memory that remembers what came before it and sometimes what came after it, depending on how you set up the LSTM. That works really well for unstructured text, and there have been great examples where deep learning neural networks have been trained on like movie reviews or the King James Bible, all of which have made it easier for these deep learning neural networks without a lot of supervision to be trained on sentiment. What we did was we said, hey, given these breakthroughs, could we train a deep learning neural network to learn how this really unstructured text is being interpreted by physicians who've already reviewed the chart. And to do that, we started with a series of experiments. It's been our experience that when we start training these deep learning neural networks, we might have a hypothesis, but it changes, as we actually construct the network. So having a detailed experiment plan with goals on how we want the inference to perform has been an essential part of what we found to be a successful way to build these models. And so we start with this experiment plan where we look at the type of text that we might be working on, and then we take different types of architectural models and see how they perform. Eventually, after we have sort of a catalog of models, we can then look at how they perform relative to each other. So it gives us a good sense of what might be the best fit for the problem we are approaching. In this example, we actually started with a lot of great work that happened in other companies. Fast text is a word embedding layer that Facebook research open sourced. And it was originally, it's trained on Wikipedia data, but we're able to retrain it on this sort of unstructured physician note data. We use a couple flavors of LSTMs, all of which we built in TensorFlow, which makes it really easy for us to implement an LSTM very quickly. And then we combine an LSTM with something called an attention model, where you're constraining the network to get a better idea of what are the specific structures in the text that might be actually driving the inference. Ultimately, all three work generally well. The LSTM plus attention seem to work best, but they're so close that we feel that after this training period, once we deploy it in production, any one of these might be able to leapfrog the other, and so we're constantly training them to see if one outperforms the other in our test data sets. This is our ROC curve, and as I mentioned, the best model was this LSTM attention model. We don't have a strong point of view of why we think that model is working better than others. We think the benefit of it, though, is that with the attention model, we can sort of check our work a little bit. We can actually present samples back to our physicians to see if the things in the notes that the model's keying off of actually reflect things that they might have picked up had they read the notes themselves. But we're excited about the fact that it's performing very well.
Sorry, what are the positives and negatives here?
So we're trying to decide if someone's justified for an inpatient stay from a reimbursement standpoint. So is there appropriate amount of complexity in that encounter to reflect an inpatient stay as regulated by CMS and other payers?
Thanks.
What you input to the model is the entire paragraph of that document.
Yes, and it's sometimes we see paragraphs, sometimes we don't, but whatever we get in that sort of field value of notes is what we're passing in as input. We did try some additional structured fields that are captured in the EMR, things like gender, age, and things like that. It provided a little bit of lift, but it didn't really change the model. We've included them, but it really ended up being the physician notes that drove that.
Is there labeling that's associated with what facility it came from, or is the text calling that?
There is labeling for the for where it came from. We didn't actually include that in our model because we wanted to see how generalizable it was. Our expectation is that we serve a certain set of hospitals today, but we'd love to serve all of them, and so we actually kept that out, and we still got pretty good results. With the attention model, we could see certain phrases and sort of a relative weighting on how important they were in the text. It's not true interpretability, but it gives us sort of a rough indication of what might be driving the classification in the network. And that's what I mentioned. That was a great, nice to have, because when we wanted to check our work with physicians, we could actually show them and highlight some of the blocks of text that were driving the model. I'll admit I'm not a data scientist, I'm a computer scientist by training, so I won't try to get too far ahead of my skis on this, but ROC has always been how we thought about model performance. Our personal experience engaging business units, and I'll talk to you about that in a second, that are actually trying to create these as products and services that we offer our customers, they will never really internalize a precision recall curve, but we found that based on what their intentions are and what they want to accomplish in their business, the area under the PR curve was a much better way for us to think about model performance. And I'll touch on that in a moment, but we really wanted to understand what's the most important charts that should be reviewed by a physician. We talked about this, what does this model do? It really pre-screens these charts for physicians to say, hey, these are the most complex cases, these are the ones that should be reviewed. If we go back to the beginning, I talked about that workflow process. Today, it's a very rudimentary workflow process. If a chart comes in, it gets reviewed. There might be some triggers or keywords that we try to prioritize our work queue on, but it was never very accurate. And so if we want to take the valuable time of a physician and make that as efficient and as well used as possible, something like this helps us understand what the trade-offs are and what we want physicians to review and what may not have a lot of high value to review. And this is a good segue into like sort of how do we think about these models for businesses. One of the biggest challenges, I think, going through this process with our business units is that, as you can imagine, they're not data scientists. And when they hear AI and we're going to build them a deep learning model, there's a great deal of excitement. But there's not a recognition that terms like accuracy and precision have very specific definitions for us in building models. And so one of the biggest challenges we found is how do we help them decide what the sort of goal line should be for our model? What are the trade-offs in inference that they're going to have to make? And how do they balance those trade-offs? And so one of the things we've been fooling around with is, actually let me take a step back. How familiar are you guys with a confusion matrix? It's an invaluable tool for us to understand the trade-offs in any prediction. But it's very hard to internalize if you're not initiated in data science or not familiar with statistical methods. One of the things we've tried to do is we've tried to overlay a histogram almost with the confusion matrix. So in this chart, I could get a sense very quickly of how accurate, how many cases are being accurately predicted to result in an inpatient stay. Those are the ones that we want a clinician to review. And then how many might actually result in an observation, which would have been a less complicated case and probably not worth their time to review. But the key question is that there's always cost with any of these reviews. There's time and effort for a physician to do them. And so as a business unit, how much do you want to include in these reviews? Like how many of these actual inpatient stays are you willing to take on, recognizing that as you move further along that threshold, or you move that threshold, the trade-off is that you're going to get more false positives. And then what cases would you have missed if you hadn't moved that all the way to the end of that axis? And what's nice about this is that now we can actually combine this with business impacts like cost or time, so that you can really understand what your trade-offs are. This threshold here is the optimal point. That's the F1 score here for this model. But that doesn't necessarily mean it's the right business decision for that unit. They may decide that they want to not miss anything and move that threshold all the way over and simply have everything covered. Or they want to move that back because they just don't have the budget or resources or people to handle that kind of volume. And these are the types of decisions where we find sort of AI meets the product and business requirements, where we want to be able to have a conversation with the product owners, with the business units to say, these are the trade-offs you need to think about when designing AI into your products and services. So what are the things we've learned from our journey in building these first models? First and foremost, and I didn't touch on this a lot, we spent a lot of time defining why someone needs artificial intelligence, what the business value for the inference that they're looking for is. What are the trade-offs and how do they impact the business? Second, we look for well-labeled data sets. We're looking for things, and because of the administrative work we've done, we've got lots of interesting well-labeled data sets where there's a very complex set of inputs and there's a person who made a decision that we can use as sort of our ground truth for that decision. We have to understand the implications of the decisions. Clinical decisions are extremely important to the care of folks. They're governed by regulation and practice. These may not be the best decisions that we want to apply deep learning for today, given all those constraints. And there's one final point. When we think about even some of the ethical considerations of these decisions, you can imagine like denying a claim could have some real negative impacts to a member or a provider. We actually try to flip the question and completely punt on that, focusing on what would be approved with this AI. Because if their approval passes through and everyone gets paid as they would expect to be, there's no friction there, there's no conflict there. And so when you think about these use cases, think about flipping the use case potentially. Look at the positive case, keep the complicated decision where there might be a denial in the hands of people with clinical judgment, in the hands of people, sort of humans in the loop, because that's where we do very well, and where these models may not reflect all the complexity of those decisions. But those are some of the things we've learned so far. If anyone has any questions, I'll be around today and tomorrow, and we're happy to share some things we've learned.